There are some math problems out there that are so tough, even our most powerful supercomputers would just grind to a halt. They involve adding up an infinite number of things that just refuse to settle down. But what if I told you that mathematicians have a secret weapon, a kind of mathematical shortcut to tame infinity and get answers with absolutely stunning speed? Okay, let's dive in. So here's where we're headed. We're going to meet a really bizarre mathematical constant, feel the agony of a calculation that barely even moves, and then, and this is the cool part, we'll uncover the elegant tricks mathematicians use to conquer it, building up to a truly powerful technique. Now, our story starts in a pretty unexpected place. Not in some fancy university lab, but with a hobbyist mathematician named Marvin Ray Burns, who, back in 1999, stumbled upon a number that behaves in a very, very strange way. Okay, so take a look at this. It's kind of wild, right? Normally, when you add up terms in a series, you expect them to zero in on a single number, but not this one. It just bounces back and forth, forever, oscillating between two different points. This is what we're calling the Constant's curious dance. So what's going on here? Well, even though the series technically never settles on a single value, it diverges, the sums are trapped. They're bouncing between a floor and a ceiling. And that upper value, the ceiling of this eternal dance, that is what we call the MRB constant. All right, so the obvious question is, why don't we just throw a computer at it, tell it to add up a billion, a trillion terms, and just call it a day, right? Well, as it turns out, for this specific problem, that is a terrible, terrible idea. And this is where things get a little crazy. I mean, what do we actually mean by slow? Are we talking go grab a coffee slow? Wait a few hours slow? Nope, not even close. Okay, get this. To get just the second decimal digit to stop wobbling, you need to add up over 1,700 terms. For the third, over 37,000 terms. And if you want just 6 measly digits of accuracy, you're looking at something about 1,000,000 terms. This is what we mean by the agony of slow convergence. Brute force just isn't going to cut it. Clearly, we need a shortcut, a smarter way to do this. And that brings us to this really cool idea called series acceleration. And one of the first and most elegant methods came from the legend himself, Leonhard Euler. So instead of just adding terms one after another, Euler's method does something really clever. It basically takes the averages of those bouncing sums we saw earlier. By repeatedly averaging the results, it has this amazing effect of canceling out all that oscillation, all that wobbling, and it gets you much closer to the true answer much, much faster. It's our first big clue that we can work smarter, not just harder. But as cool as Euler's trick is, it was really just the opening act. Now we get to the main event, a technique that doesn't just speed up the adding, it actually improves the things we're adding in the first place. You see, the real bottleneck in our series is that pesky little term n to the power of 1 over n. It's a complicated function to calculate over and over. So the big question became, what if we could find a simpler function that could act as its stunt double, a near-perfect mimic? And this is the potty breakthrough. It is brilliant. Think of it like this. A normal approximation is like trying to trace a complex curve with a straight ruler. Sure, it might match for a tiny little section, but it quickly goes off track. A potty approximate, on the other hand, is like a flexible ruler. It uses a fraction made of 2 polynomials, and that structure allows it to bend and shape itself to hug the original curve almost perfectly over a much, much wider range. And you can see it right here. That blue line is our tricky function. The yellow one is a simple approximation. It's okay, but you can clearly see the gap. A potty approximate, though, creates a kind of shadow function that traces that blue line so closely they become almost indistinguishable. This means every calculation we do with it is vastly more accurate from the start. So now for the magic. What happens when you combine this super accurate Pade approximation with a really souped-up summation algorithm? Well, you get computational lightning in a bottle. It's like a 1-2 punch. First, you use the efficient Pade approximate, we'll call it the kernel, to do all the heavy lifting, calculating those tricky values with amazing precision. Then, you take those super accurate numbers and you feed them into a powerful summation algorithm to add them all up, which zooms you right to the final answer. And the payoff? I mean, the results speak for themselves. With just 60 terms, brute force gets you, maybe 2 correct digits? The classic Euler transform does a lot better, gets you a respectable 22. But Crandall's formula, which combines these Pade and Euler ideas, gives you an incredible, mind-blowing 111 correct digits from the exact same number of terms. The jump in efficiency is just off the charts. And this picture just says it all, doesn't it? On the left, that's the brute force sum. It's chaotic, it's messy, it's bouncing all over the place. On the right, with the accelerated method, the convergence is smooth, it's swift, it's decisive. It just locks onto the true value almost immediately. No drama. Thanks to this kind of mathematical wizardry, a calculation that was once practically impossible has been totally conquered. As of 2022, the MRB constant is known to over 6.5 million decimal places. So why does all this matter? I mean, cool story, but it's just one weird number, right? Well, this is about way more than the MRB constant. This whole toolkit, this ability to accelerate the convergence of a series, is a fundamental part of modern science and engineering. Seriously, this stuff is everywhere. Anytime you have a complex problem that involves adding up tons of little pieces, you'll find these ideas at work. We're talking physics simulations, financial modeling, the signal processing that makes your phone work. You name it. This is the secret sauce that lets us get fast, accurate answers to otherwise impossible problems. And I think this quote from Burns and Perez just nails it. You have the geometry that explains why the problem is so weird, you have the analysis that tells you how it behaves, and then you have these brilliant schemes that give you the practical tools to actually solve it. It's a beautiful fusion of ideas. At the end of the day, this whole story is bigger than just one number. It's a testament to human ingenuity. And it really makes you wonder, doesn't it? What other problems that seem impossible today are just waiting for the next clever mathematical shortcut to be discovered?